In previous models, we had shown that there are two types of data, continuous or numerical data, as well as categorical data. The aim of this module is to describe random variables in terms of these probability distributions. Categorical random variables, such as gender and eye color, or other count data, such as number of chairs or tables in a room, are called discrete random variables. Remember that discrete means separate, and thus each entry or numerical value is separated from the others. The numbers between the whole numbers are meaningless, such as 1.5 chairs. Having a half a chair may be something we have in our homes, but it doesn't give us anything that we can really use to actually count with. So we'll only have probabilities for each category, such as male or female, high or low. Numerical random variables are called continuous random variables. All values between each whole number will have a probability assessed. So in our data set, we may collect a various number of heights of students, and we could actually calculate the probability of having someone with a 68.27 inch height, even though we may not have had such person of such height in our data set. On the bottom left, you'll see a graph for a discrete random variable. You can see how we have these individual bars corresponding to each level, 1, 2, 3, 4, 5. And this is what a discrete random variable probability distribution looks like. On the right side, we have a continuous random variable probability distribution, which is a smooth curve, which is giving you all of the individual points between every point. In this case, we have a normal distribution where we see the mean in the middle at around 98.6, and every single point for human body temperature is assessed a relative probability. Since all probabilities are a number from 0 to 1, it should be pretty clear that if we add all the probabilities for every event in a set, the sum of the probabilities will equal to 1. In addition, there can be no negative probabilities. Negative probability wouldn't make any sense. Therefore, there are two properties for a random variable. Adding up all of the individual probabilities for every single event will equal to 1, and all of the probabilities will lie between 0 and 1 inclusive. If we add all the probabilities, we would get what's called a cumulative probability. From the equation above, if we add all of the probabilities, we get a cumulative probability of 1. However, we can examine only cumulative probabilities for a smaller set of events, such as the cumulative probability of rolling a 1, 2, or 3 on a dice. In this example, we would get the following cumulative probability. Probability of x equal to 1 is 1/6, of x equal 2 is 1/6, of x equal 3 is 1/6, which can mean that if we're looking for a cumulative probability, we're looking for the probability of 1, 2, or 3, which is equal to the probability of x less than or equal to 3, which would sum up all of the individual probabilities, giving us the cumulative probability of 1/2. One example of the cumulative probability distribution is the normal bell curve. On the left, we have a graphical example of our bell curve. From the graph, if we draw a line at the mean, we can see that 50% of the curve is below the mean and 50% is above the mean. So we can say that the probability of x that is less than mu, which is our population mean, is equal to 0.5, 50% below. On the right, what we then do is we can represent the cumulative probabilities of the normal distribution, and it would look like this S-curve. And the reason it looks like this S-curve is because if you see, the bottom part starts very low to 0, which means all of the values that are very low will have a very, very small chance of occurring. And as we get closer and closer and closer to a mean value, which in this case is denoted as 0, the red dashed line across represents the 0.50. 50% of the probability will lie to the left of the 0. As we continue to add more probabilities, the line will curve upward, and it will basically be asymptotic or tend to 1 at the very top, 1.0, as we continue getting more data to the right. So this is how a cumulative distribution might look. In a previous model, the concept of descriptive measures such as mean, variance, and standard deviation were shown. These measures can be expressed in terms of the probabilities of random variables. A mean is really an expected value, which we denote as E of x, the expected value of x. And it's classified, or can be classified, as the sum of weighted probabilities, especially in a discrete sense, which is what we're looking at here. Again, being discrete, we have the individual values of 1, 2, 3, 4, and 5. The table on the right shows 5 possible values and the count of each value. Adding up the total count, we have 60 observations. Therefore, the probability of each value is given in the third column. To calculate the expected value or mean, we use the following formula. We say mu is equal to the expected value of x, which is equal to the sum symbol, of each individual x, times its own probability. So if the value of xi is 1, we will multiply it by the probability of having a 1, which is 0.167. And if the x value is 2, we'll multiply that by the probability of xi, which is 0.20. And then we'll have 3 times 0.133, 4 times 0.233, 5 times 0.267. We add them up and we will get a mean value of 3.233. Similarly, we can compute a variance in a likewise fashion. But for the variance, we need to find the difference between each xi and the expected value. And remember, the reason we did this is because with the variance, we're looking for how far the dispersion is around the mean. Since our mean is our expected value, we're basically looking for the difference between each xi and the expected value. Remember that we square this so that we can get rid of negative numbers, and we also square it because it will magnify the effect of greater dispersed observations. The further it is away, by squaring it, it makes the number even bigger. So using the same table as before, we calculate the variance using the following formula. Again, we'll use sigma squared, which is equal to the variance of x. We will add up each of the individual pieces, which is xi minus the expected value of x, which we've done before in the previous slide is 3.233, and we will square it. We'll then multiply it by the probability of xi. So in the first case, we will have 1 minus 3.233, square it, and then multiply it by 0.167. Then for the second one, we'll take 2, subtract 3.233, square it, and then multiply it by 0.200. And we'll continue this all the way up through 5. And when we do that and we add them all together, we will end up with 2.11. Alternatively, there's another formula here where it's the same thing. It's just a little math factoring that's done. We have the sum of each xi squared multiplied by the probability of that xi, and then we subtract the mu squared. We'll get the same answer, but it's a little bit more mathematical, and it's a little bit more, it's actually a little bit more concise. However, again, we won't have to do this because Excel will actually do this for you. Now, the standard deviation is used again as a better measure for interpretation than the variance, and it's the same as it was in previous slides. It's simply the square root of the variance. So all we simply need to do is take the square root of the variance calculated on the previous page, which was 2.11, take the square root, and we get 1.45 to understand the standard deviation.